triple integrals end up being conceptually pretty similar to double integrals, except that there is more to do since there is that third integral, but also there are more options. Whereas with a double integral, at least if it's in rectangular coordinates, it's either dx dy or dy dx, and that's it, right? Those are your only two options for the orders of integration. Here you have six, because if you start with z, then you could go yx or xy. And then if you start with y, you got two options. You start with x, you got two options. So there are more possibilities. And the other thing is that because you're integrating over a three-dimensional region, with all those different possibilities, there will be ones sometimes that are significantly harder than others, just with different orders, even if you're integrating over the same function. And that's a thing where I think you just have to do a few of them to kind of get used to that and to think, okay, if I go this way, it's going to be easier than if I go this way. But this first thing with Fubini's theorem, that part that I just said actually doesn't matter, because if it's just a rectangular solid where in this definition of D, so our book uses a D instead of an R. So I guess D when it's three-dimensional and R when it's two-dimensional. But here, like the A, the B, the C, the D, and the E, and the F are all supposed to be numbers. So then it's just a rectangular solid, and all of the orders are going to be, I guess, equally difficult or equally easy, depending on which way you want to look at that. But then the integration is more or less what you would expect it to be. You work inside out, just like you would with double integrals, and there's just more of it because you have the third integral now. So just going down here to where this example is, just to kind of see how this works. If we want the triple integral of xyz squared, and we're integrating over D, where that's the rectangular solid defined this way. So where x is between 0 and 1, y is between -1 and 2, and then z is between 0 and 3. So I did it in the order dz, dx, dy, just because I was thinking, because with z and x, the lower limit is 0 in both cases. If I do those first, I might be able to shorten this a little. So the order really is going to be the same degree of difficulty, whichever one of the six ways you pick. But that was why I picked this one. So, all right, well, we're going to integrate that with respect to z first. So, all right, you integrate z squared with respect to z, it's 1/3 z cubed, right? Double evaluate at 0 and 3. So, all right, the 3, that's going to give you 27 over 3, which is 9, and then the 0 is not going to give you anything. So you get 9xy, and then this just turns into the regular old double integrals like we used to have a couple sections ago. So then you integrate with respect to x. So, okay, x squared over 2, double evaluate that one, and that ends up being 9/2 y dy. Integrate that, evaluate it, eventually you get 27/4. That one doesn't seem that bad. And usually the integration itself is not the tough part. Usually the tough part is in the setup. And you'll see what I mean when we get into general regions, not just rectangular solids. So with a general bounded region, and I guess I had to pick one, like one of the six possible orders of integration. So I just stuck with the usual dz, dy, dx, which I think would be the thing that most people would pick left to their own devices. So if x is between two numbers, right? So a and b are just two numbers. But then y is bounded by two functions of x. So we've seen that part before, right? Where we just have x bounded by a couple of numbers and then y bounded by a couple of functions, right? We had double integrals like that. But now we also have this, where z is bounded by two functions of x and y. So how does this work? Well, what you want to do in this case is you want to integrate in a manner that as you go through the integration, it's almost like you shed variables. So I'm going dz, dy, dx. So when I integrate with respect to z, then when I evaluate whatever I get after I integrate, then I'm going to sub in these functions of x and y. But then I'm going to integrate with respect to y, and then substitute in these functions with respect to x. And at that point, the only variable you'd be left with is x. And then you integrate that, put some numbers in there, and then you're done, right? So look at how that works. So you got functions of two variables, functions of a single variable, numbers. And generally that's the game plan. You want to do it that way where like you decrease the number of variables as you go through it. And that's the setup that you use to get there. And then for any of the other 5 orders of integration, it kind of works the same way. It's still that same overall thing. You want to reduce the number of variables as you go through the integration. So just to go through what one of these integrals looks like, and then we'll worry about how to put the limits together and all that. So we're going to integrate 2xy, and then the order is going to be z, then y, then x. And so notice z's bounds, right? This is clearly a function of x and y, right? And then the bounds for y, functions of x, right? 2 linear functions of x. And then bounds for x is just a couple of numbers. So if we go through and do it, the integration is really not that bad, right? You're going to integrate 2xy with respect to z. Okay, well then that'll just give you that z that you've got to evaluate. And then the only thing that'll give you anything is when you sub in x plus y, which is right there. And then I distributed the x plus y, and then integrated right here with respect to y. And then subbing in 2x, subbing in x, right? Here's the part with the 2x, and then inside the parentheses is subbing in x. And then every term has an x to the 4th in it, so we can combine all the terms together. So I did the integer ones and the non-integer ones, and then put them together, right? Since that's 9 thirds and 14 thirds, which will give you the 23 thirds. And then you integrate that with respect to x, and then sub in a 1, you get 23/15. You sub in a 0, you get 0. So the answer is 23/15. Okay, so the integration itself, it's not too bad. Maybe it's a little bit more abstract because in that first integration you have the extra variable in there, right? So you got x and y, but it's still the same overall concept. And the tough part isn't this integration down here. The tough part is getting to this thing. Like just having the limits of integration written out correctly, that's the hard part. And so really that's the next thing that we're going to focus on, more than the integration really, even though we're still going to do the integration. This picture is looking a little bit grainy, but that's because at this point it's a copy of a copy. Because I took a picture of it and stuck it into the original file and then wrote everything in after printing it out and then took a scan of that. So that's what's making this a little bit grainy, but I think it's still clear enough to where you can see where the different surfaces are that make up this shape. And that's really kind of the important thing. So the way that this integration here is set up, it's the usual dz, dy, dx. And the thing that we're supposed to do, I guess, ultimately is rewrite that triple integral using the 5 other orders. But how do you get here first of all? So just this one that's here already. Well, basically what you would do for whatever variable you're going to start with, so whatever variable you're going to integrate with respect to first, is you just see, is there a clear-cut way where you can tell, like if it was going to be for x, like what's on the back and what's on the front, or if it's for y, what's on the left and what's on the right, or it's for z, if you're going to do that first, what's on the top and what's on the bottom. What's on the top and what's on the bottom, just kind of eyeballing this picture, you can see them pretty clearly because the bottom is z equals 0, right? This thing is all in the first octant. So looking at it, you go, yeah, that's what it looks like, right? It looks like the bottom of this figure is like right in the xy plane. So that's where z equals 0. That's why there's a 0 right there as a limit of integration. And then the top is this, right? This is always the highest part of this figure. So it looks like you've got 1 minus y on top, 0 on the bottom. That's where these limits of integration come from. And then basically it's like once you've got that, then what you do is you project that figure down into the xy plane. So the plane involving those other 2 variables. So if you do that, then what you get is actually this thing right here, where then clearly the origin's part of it, 1, 1 is part of it. This point out here is, or the origin, that's 0, 1, and then that's 1, 1, right? This point out here. So what you end up with then is that if you kind of rotate this a little bit, so it's the usual way with x horizontal and y vertical that you usually would draw the xy plane, then you would have y equals radical x as the bottom of this thing, and then y equals 1 as the top, and then right, x equals 0 over here is the other boundary. So then if you look at that and you go, okay, well then if we're going to go y next, then if you do it off of this projection, which is the way that you're supposed to do it, you go, okay, well the top is 1, so there's that limit of integration up there, there's the 1. And then the bottom of this is y equals radical x, right? It's this curve right here. So radical x on the bottom. And then the x values are going from 0 to 1, so 0 to 1 for the limits of integration for x. And that's where that one comes from. So what if you change the order from dz dy dx to dz dx dy? That seems like of the other 5, that would be the easiest one to get. Well, when you integrate first with respect to z, that wouldn't change anything. You're going to have the same limits of integration. Since you're starting off with z, it's not going to affect that, right? The changes are out here. And if you go the other way, then you're going horizontally first, then vertically. So horizontally, then for the dx part, for integrating with respect to x, you go, well, 0, x equals 0 is what's on the left side. And then what's on the right side is this, which is y equals radical x, or to solve that for x, you have x equals y squared. So since that's the part that's on the right, that's going to be the upper limit of integration, right? That's the going left to right, the upper side is toward the right. And then the lower is going to be 0, because it's just the axis right there. And then the y values go from 0 to 1, so 0 to 1 for the limits of integration for y. So yeah, that one isn't too bad to get from the first one that's already there. The next one that I did is if you integrate with respect to y first. And if you're going to do that, and the reason I'm up here by the picture is because you need to figure out what's on the left and what's on the right. Well, the thing that's always on the left, it's this surface here, which is labeled down here as y equals radical x. So, okay, that's on the left. The thing that's on the right is this over here. And it would be better if that was solved for y. So it is this. It is z equals 1 minus y. But when we go down below, I'm going to have that written as y equals 1 minus z, which is the same thing, just solved for y. But if I go down here, so y equals radical x is on the left side. It's the surface that's always on the left of that solid up there. And then y equals 1 minus z is always on the right. So we know what our bounds are going to be when we first integrate with respect to y. It's going to be radical x on the bottom. It's going to be y, or 1 minus z on top. All right. Well, then projecting into the xz plane, if I scroll back up for a second. So the xz plane, I guess it's kind of over here. And this is a tougher one to see, right? Because like if you look at this, like the YZ plane, like that projection is really easy to see. And even the XY plane, like you can see it because it's kind of like flat on the bottom there. But the XZ projection is a little bit tougher to see. One thing that you can tell is that it's kind of going to be this surface over here kind of smushed, like flattened up against this plane over here. So we're going to need to know what this line right here that I'm tracing is. And that's where the surface on the left and the surface on the right intersect. So to figure out what that is, it would have to be where these are going to match up. So basically what I did is I said, well, the y values are going to have to match. So then y equals 1 minus z, we got y equals radical x. So radical x has to equal 1 minus z. And that's what this is. And at least that's what it's going to be when it's flattened up in that plane. So for the xz plane projection, that's what I did right here. We had the y equals radical x. That's the thing that's on the left side. Z equals 1 minus y is on the right. So I just said, okay, I'm going to sub the radical x in for y and say z equals 1 minus radical x. And then this is oriented differently because I guess I wanted to put the x-axis where it usually is when you have something that's two-dimensional. So like the positive x-axis toward the right. You don't have to draw it this way. If you wanted to draw it the other way with the positive x-axis toward the left, that would kind of look more like a three-dimensional picture. Although if it makes it harder for me, but if it makes it easier for you, then do it like that, I suppose. Then z equals 1 minus radical x, it looks like this, right? And especially because we know what some of the points are. Like if I go back up here for a second, like we know that the point 0, 1, just in terms of x and z, so 0, 0, 1 in 3 space, but 0, 1 with just the 2 points, that's got to be on there. And then this point right here, which I guess really it's 1, 1, 0 when it's in 3 space, but when it gets projected over here, you lose the y coordinate, and it's just going to be 1, 0. So that's what we've got here, right? There's 0, 1, there's 1, 0, and then there's that shape, the 1 minus radical x. And so then if z is 1 minus radical x, then radical x is going to be 1 minus z, or x is 1 minus z quantity squared. This piece you don't need for this one that's down here that's visible. You need it for the one that's under the dotted red line. But we'll get there in a second. So if we're going to go dy, dz, dx, we knew what the limits of integration were going to be for y, right? Because you got the radical x on the left, you got the 1 minus z on the right. Then after that, if we're going to go z next, then we're into this projection. And then we go, well, the thing that's on top is 1 minus radical x, so that's the upper limit. The thing that's on the bottom is going to be z equals 0, so that's the lower limit. And then the x values are going from 0 to 1, so 0 to 1. There's that order. Now, the other one that starts with a y, so if you go dy, dx, dz, so same limits of integration for y, but then if we're going to go dx next, then it's going to be what's on the right and what's on the left. So the thing that's on the left here is x equals 0. So, right, and that's what the y-axis is. So there's the 0 down there. The thing that's on the right, it's this line, but you want it solved for x, right? Since these are the limits of integration with respect to x. So that's really what this is for. So the x equals 1 minus z quantity squared. So that's really what we need. So 1 minus z quantity squared is going to be the upper limit of integration. And then the z values are going from 0 to 1. All right, there's 4 of them, 2 left. The next one is going to be if you integrate with respect to x first. So if you're going to do that, you got to figure out what's in the back and what's in the front. Well, you can pretty clearly tell if this doesn't go back on the other side of the y-axis. So there are no negative x values here, and it looks like the yz plane is what's on the back, like it's the rear boundary of this thing. And the yz plane is also known as x equals 0. So that's what's in the back. The thing that's in the front, because you have to think about going forward that way along the x-axis, it's this thing right here. It was the thing that was on the left when we were integrating with respect to y, when we were going y first. So here, it is y equals radical x. We're going to end up writing that as x equals y squared, just because if we're integrating with respect to x, we need the limits to be solved for x. So if I go down here, so integrating with respect to x first, x equals 0 is in the back, and then x equals y squared is in front. So then those are going to be our limits for x, and if you go down here, you can see them, right? There's 0, the lower limit, y squared is the upper limit. And then we have to have the projection into the yz plane, and that one you can see. Like if I scroll back up, the yz plane, I mean, you can see it, and you go, oh yeah, there's that triangle right there. So that one actually might be the easiest of all of them, I guess of the 3 options for what to start with, because the plane projection that you would then need is just like right there in the picture. You can see it, and that really, really helps. So just looking at the picture, you can say, okay, well, we know it's going through 0, 1, 0, and then 0, 0, 1. But then when you get rid of x, then this is just 1, 0, and 0, 1. And then this line right here is z equals 1 minus y, right, which we can get from the original picture. But then when we go, I guess, in the order of y before z, we're going to need it this way. But first, I went dx, dz, dy. So if it's going to be dz, dy, then for dz, we've got to figure out what's on top, what's on the bottom. So what's on top is 1 minus y, and then what's on the bottom is z equals 0. So 1 minus y for the upper limit, 0 for the lower. And then the y values are going from 0 to 1. Last one, if you change the order to be dy, dz at the end, then looking at this thing, it would be what's on the left versus what's on the right for the dy portion of this. So what's on the left is y equals 0, and what's on the right is going to be this line right here. So it's z equals 1 minus y, but you want that solved for y. So y equals 1 minus z, and that's our upper limit. And then the z values are going from 0 to 1. There. That's all of them. It's a lot of work to get all 6, but you would never realistically have to do all 6. If you can do one of them, you'll get the same answer every time, like if you need to do the integration all the way out. So just pick one where you don't have to like break up a triple integral into 2 triple integrals. I think that would be good advice, but I think it's worth it to go through one of these where we exhaustively hit every possibility. So this fourth example doesn't have a picture. It tells us what we need to do. We've got to integrate z over region D, where D is the solid tetrahedron bounded by x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, the thing that really helps here is having the picture. And this one's not that terrible to draw, but if you're going to draw a picture, I would say really you probably want 2 of them. First, draw the thing that you're going to integrate over. So like the full solid region. So here, this tetrahedron, drawing this is not too bad. So we'll get that one. And then once you kind of eyeball that and figure out which order of integration you're going to use, then you also probably want a 2-dimensional projection, like the one that you're going to need. So like if you're going to go dz, dy, dx, you're going to want the projection of the xy plane. So like the last 2 variables. So the 2 dimensions that you want would correspond to the last 2 variables that you're going to integrate with respect to. Right? So then here, dx, dz, dy, you want the yz plane. Dy, dx, dz, you want the xz plane, right? Since x and z are going to be the last 2. So what I did was first I just drew the tetrahedron. And I guess really I just drew x plus y plus z equals 1, kind of imagined the rest of it. Right? Because 1, 0, 0, 0, 1, 0, and 0, 0, 1 are all going to be part of that plane right there. So we can get those, right? So those, like once you draw those in and connect them, then you can basically see the whole tetrahedron, right? Because it's almost like you can see through the front to see the left side and the back side and the bottom. And then I kind of looked at this and I went, okay, well, I know what's on top and what's on the bottom, right? Because the bottom is clearly z equals 0. And I know it says it up toward the top too, but that's what it is. And then the top is going to be the x plus y plus z equals 1. So I said, okay, well, if that's the top and the bottom, and then I have to project onto the xy plane, because if I'm doing top and bottom, that's z. So then I'm going z first. But the projection onto the xy plane looks really easy because you can basically see it right here, right? You can like see the bottom through the front of that tetrahedron, and the bottom is the part that's in the xy plane. So you go, all right, I can see that. This doesn't look like it's going to be too bad. So what I ended up doing is I said, all right, if that's the top, I got to solve that for z eventually because that's how I need it for the limit of integration. And then the bottom's just z equals 0 to do anything there. But in the xy plane projection, you go up here and you say, okay, well, if we just didn't have a z, then that's 1, 0, that's 0, 1. So 1, 0, 0, 1, and you get that triangle. And that would either be x plus y equals 1, or because I'm going to just do dz, dy, dx, that's why I've got the solve for y, because then I'll have limits going from 0 up to 1 minus x. And then I guess for x from 0 to 1. Another thing that might be worth noticing is another way that you can get this equation right here is just to say that, well, if it's in the xy plane, then z has to be 0. So this is really just x plus y plus z equals 1 where z equals 0. So that is another way to think about it too. Although here, when you can see it right there in the original 3-dimensional picture, maybe you don't need to take that step, but it's another way of looking at it. So, okay, we're going to integrate z with respect to that region D, that 3-dimensional region. So what I did was I wrote this intermediate step in where I said, okay, first we're going to integrate with respect to z. So top and bottom, the bottom is 0, the top is 1 minus y minus x. And then from there, we had to figure out r, the two-dimensional projection into the xy plane. And then I'm going dy dz, which is why I've got 1 minus x for the top, and then 0 for the bottom, and the x values go from 0 to 1. All right. Then the integration itself is not too bad, right? So you integrate z, I guess with respect to z, you get 1/2 z squared. Double evaluate that. I pulled the 1/2 out front, and then I did a u substitution instead of multiplying this out because it actually makes some of the later stuff faster. So I said if u is the thing in parentheses, then du is negative dy, which means I need a minus in there. So I need a minus out front. And so then I can integrate, and you end up with 1/3 u cubed, right? So 1/3 times 1 minus y minus x quantity cubed. And then we're going to double evaluate that one. And then, let's see, if you sub 1 minus x in for y, you get this. And then if you sub in 0, you get this. Notice this thing here, the 1 minus the quantity 1 minus x, that's 0. Right? Because that's 1 minus x minus the quantity 1 minus x. So that's not even here down here because I just went, oh, that's a 0. And then you just have this other part, the negation of 1 minus x quantity cubed. Then I brought that negative sign out front. So it's just going to be 1/6 times the integral from 0 to 1 of 1 minus x quantity cubed dx. And then I guess that's another u substitution. That's the way that I looked at it. I said, well, if u is 1 minus x, then we're going to need a negative in there and then negative out front. So there's the negative that you're left with after you integrate, the one that would be out front. 1 minus x raised to the 4th power over 4. And then let's see, if you sub in 1, you get 0. If you sub in 0, you'll get, well, negative 1/4. So 0 minus negative 1/4 is just positive 1/4. Multiplied by 1/6, 1/24. All right. So a lot of it is actually in the beginning, right? Most of the work is not really in the integration. I think most of the work is basically just sketching this out, figuring out your plan of attack as far as like what variable you're going to do first when you do the integration, and then drawing out the projection and really getting to this point. When you get to this point right here, where you've got the limits of integration all set up, then it's kind of downhill from there usually, because the integration typically is not that insane. So the setup, I think, at least conceptually, is most of the work here. Example number 5, not the greatest paraboloid that I've ever drawn. The one on my scratch copy actually looks way better somehow. This one, it almost looks like I tried to draw a turnip or something and just didn't really get there at all. But that's supposed to be a paraboloid, opening that way, right? So starting at the origin and then coming out like that. The D here that we're integrating over, it's the region bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 4. So it would just stop right there. All right, so what I thought, because we're given these bounds right here, and they're both relating to y, is I said, oh, well then, if we know that y equals 4 is the bound, that's over here, that's on the right side. So the thing that's on the right is that, and then what's on the left is this. So this is already kind of set up for us if you want to start integrating with respect to y. So I thought, these things are long enough. We don't need to be making extra work. We might as well just take what we're being given here and say, all right, well, that's the thing that's on the left, the paraboloid, and then on the right you have y equals 4. And so then that means that y is between x squared plus z squared and 4. So good, there are limits of integration with respect to y. Then we're going to have to project into the xz plane. But if you look at this thing, and I know this does not look like much of a circle here, but if you flatten that up against the xz plane, that is what you would get, right? I mean, if it's x squared plus z squared equals 4, which is where the paraboloid and then the plane y equals 4 are going to intersect, right? Because it would be when the two y's are equal. So x squared plus z squared equals 4 is a circle. It doesn't look like one in my paraboloid, but I guess, don't take that as a literal good drawing or anything. Right, that's just a circle centered at the origin with radius 2, right? It's this. So then if we're going to integrate with, I guess I have it set up to go with respect to z and then with respect to x. So I said, all right, well then the top is the positive square root of 4 minus x squared, and the bottom is the negative square root. And so we can set it up like that, and then the x values are going from negative 2 to positive 2, right? So right there are my limits for y, because we said 4 was on the right and x squared plus z squared was on the left. And then going to the xz projection, we have the top and the bottom with those roots, and then the x values are going from negative 2 up to 2. So first, integrating with respect to y, that's easy since there's no y in here, right? You just have that square root times y, double evaluate that. And then you say, all right, well, it's 4 times that square root minus x squared plus z squared times that square root. This integration looks rough. So what I said is I looked at this thing and I went, wait a minute, x squared plus z squared, that's r squared if you flip to polar coordinates, and it's here, it's here, it's here. Oh, and then you look at these and you go, we could end up with things that are a whole lot less ugly if we switch to polar coordinates. So you don't have to switch the polar coordinates here, but it will make your life a lot easier. So I did it, and I said, by definition, r is the square root of x squared plus z squared. So that square root, that's an r. This is an r squared, right? So that's that right there. This square root's another r. And then when we switch, you're going to end up with r dr d theta. So again, from the last section, don't forget that r right there. And then we just have to get the limits for r and for theta. If I go back up to the picture, this is a circle of radius 2. So r goes from 0 out to 2. And then for theta, it goes all the way around. So 0 to 2 pi, right? So 0 to 2 for r, 0 to 2 pi for theta. Clean this up a little bit. This ends up being 4r squared minus r to the fourth. And then the integration is not too bad. I did kind of this fancy maneuver here because I never do this, and it is a legitimate move. And I don't know why, it just never occurs to me to do this sort of thing. But if you can break up the thing that you're integrating into a product of just something in r and something in theta, and I said, yeah, the thing in brackets is in r, and then times 1, right? And the 1 is the thing that's in terms of theta. So then you can break this up into the product of two integrals. So then just integrating d theta from 0 to 2 pi, and that's just going to be pi, right? It's going to be 2 pi, or 2 pi rather, it's 2 pi minus 0. And then this, and we can integrate that without too much trouble. You get the 4/3 r to the third minus 1/5 r to the fifth. And then, let's see, subbing in 2's, right, there's 2 cubed, there's 2 to the fifth. And simplifying that, eventually you have to get a common denominator, which is going to be 15. So you end up with 64 over 15 for that, then multiplied by 2 pi, and you get 128 over 15 pi. Or I guess 128 pi over 15, if you want to write it like that. But this is one where the integration could be nasty, but this is why that polar coordinate section is in there before the triple integrals. Because sometimes when you get down to those last two integrals, that actually ends up being really helpful to be able to switch coordinate systems. Example number 6. This was a subtle enough drawing that I put the actual one in from a book, because getting this surface on what I guess is sort of the left side here, that's really hard to draw because it's such like a little sliver. But our bounds are the planes x plus 2y plus z equals 2. Right? That's the one that's over here, sort of toward the right. X equals 2y, which is the sliver on the left. X equals 0 and on the back, and then z equals 0 on the bottom. Okay, so as far as trying to figure out a battle plan for what you're going to do first, the word to the wise, I guess, would be don't start with a variable that would force you to break the triple integral in two triple integrals right away. So what I'm saying is don't start with x. Because if you try to start with x, you go, oh, well, the back is easy. It's x equals 0. Yeah, the back is easy. The front's not, because what's in front? Sometimes what's in front is this, the x equals 2y. Sometimes what's in front is this, the x plus 2y plus z equals 2. So what you'd have to do is you'd have to break it up based on this point. So the 1, 1/2, 0. And you have to say, all right, well then we're going to basically have a left side and a right side. So you got to split the triple integral into two triple integrals. So anything like that that would involve a split on the first variable, I would avoid that at all costs. So I looked at that and I thought, okay, front to back, I don't like it. It looks harder than it has to be. You could do left side, right side, because you could say, oh, the left side is clearly this and the right side is clearly this, and that would work. I did it as top and bottom because this thing that's on the left, it's never on the top. This is always the thing that's on the top. So I said, okay, if this is always what's on top, and we know the bottom is z equals 0, I think I can work with that. So the top is x plus 2y plus z equals 2, or then like that if it's solved for z. Bottom is z equals 0. And then you need the projection into the other two variables, into that plane, so the xy plane. And you can see it here. Right? The xy plane projection, you can see it. You'd have the origin, you'd have the point 1, 1/2, if you're just using x and y and ignoring z for now. And then you have the point 0, 1. Origin, 1, 1/2, 0, 1, and it's that triangle right there. And then you say, okay, well then what's on the bottom, what's on the top? The bottom is this over here. So that's x equals 2y. Right, so x equals 2y is on the bottom, or y equals 1/2 x. And then the top is going to be this right here. And so that's x plus 2y equals 2. Right, because if we're in the xy plane, z is 0. So x plus 2y equals 2, or solve for y, it's y equals 1 minus 1/2 x. When you get here, again, you have to kind of think which way is going to be easier. I thought going with respect to y and then respect to x would be easier, because if you go with respect to y, it's pretty clear what's on the top and what's on the bottom. Right? What's on top is always this. What's on the bottom is always going to be this. If you go, I guess, dz, dx, dy, so if you're going to go x first and then y, then you have to worry about what's on the left and what's on the right. What's on the left is always x equals 0, but what's on the right is sometimes this and it's sometimes that. So you end up having to break that up into two separate integrals. So I like to avoid the breaking up into separate integrals if I can. So that's why I said, all right, I'm going to go dz, then dy, then dx. Because with y, it's always this on top, it's always this on the bottom. And all right, so we go down here. So I guess my first step is I just have the limits for z set up first. And then, all right, the integral of 1 dz and then dA, however we're going to set that up. But we already kind of know that. We're going to go dy dx. And then lower limit for y is 1/2 x. Upper limit for y is 1 minus 1/2 x, just like in the picture up here. Then the x values are going from 0 to 1, right? Which we can see right there, right? It's the length of that triangle. Horizontally. So, all right, then we can go through the integration. So let's see, integrating with respect to z, that part's pretty fast, where you just end up with 2 minus x minus 2y dy dx. And then we just have a double integral that we've got to deal with. So then integrating with respect to y, and then subbing in and simplifying. This actually requires a decent amount of work. You got to sub in 1 minus 1/2 x in 3 spots, and then 1/2 x in 3 spots. You do have to square a 1 minus 1/2 x at one point, so that'll give you a couple of extra terms. But I just multiplied everything out and then combined like terms. It actually looks not unreasonable here. And then that's pretty easy to integrate. And you substitute in 1 minus 1 plus 1/3, you get 1/3. Okay, so that is the final answer, you get 1/3. There are other orders of integration that are kind of brutal. The worst is dx, dz, dy. It's so difficult to do it that way that it's actually not worth going through. Because even when you get to the YZ plane projection, you end up having to do a bunch of extra work with this one. And in the interest of full disclosure, I caught that right away because when I took Calc 3, it wasn't this exact problem, but it was one that was very similar. And we had to do it in an order like that, where it was so hard to try to remember like all these little intricate things that you wouldn't need if you just used a different order. Now, why does this picture look so much better than the other two? I don't know. They're all from the same book, and I took all three pictures at the same time. But I guess the other book that I took this one out of, it calls the region E instead of D, so I guess just pretend that that's a D right there. But we want to find the volume of that solid right here, bounded by the parabolic cylinder, x equals y squared, and then the planes x equals z, z equals 0, and x equals 1. The top and the bottom are given pretty explicitly here, or even without the picture. You could say, well, all right, then z equals 0 has got to be the bottom, z equals x is the top, okay, sure. And in the picture, you can clearly see it. And then the other thing that you can clearly see, if you're going to go dz first, if you're going to take one of those orders, is the projection into the xy plane, you can see it, right? If you flatten that thing down, you go, oh, it's a parabola. Well, yeah, it's x equals y squared, right? Which is a parabola. So the xy plane projection, it's a parabola that would open toward the right. So it's sort of a sideways parabola, but then it's cut off where x equals 1, right? So that's x equals 1 right there. And then there's the sideways parabola, and it's that region. So I thought it would be easier to then integrate with respect to x before y, because looking at this thing, I thought, well, then you just have to get the bounds on the left and the right. The bound on the right is easy. It's x equals 1. And the bound on the left, it's x equals y squared, right? We already have that solved. You can do it top and bottom, so you could do dy second if you wanted to. I guess then you would end up with the square root of x on top and negative square root of x on the bottom. That's fine. I don't think that would cause trouble. But the way that I saw it right away was like that. So I guess I sort of thought first thought, best thought or something. But then if we're going to get the volume, we know that z goes from 0 to x. We already figured that part out. Then the left and right bounds, if we're going to go dx second. So on the left, we've got x equals y squared. On the right, we've got x equals 1. And then the y values, you can see them in the picture up here going from -1 up to +1. So there are those limits of integration. And then we've got to actually go through and do the integration. So, okay, we integrate with respect to z. Got to double evaluate that as 0 and x. That ultimately is just an x. Integrate that with respect to x. You get 1/2 x squared. Double evaluate that one. Then I pulled the 1/2 out front, and I said, all right, 1 squared is 1. Y squared is y to the 4th. Then we've got to integrate that with respect to y. So there's that. Double evaluate it. And you end up with 1/2 times the quantity 2 minus 2/5, right? So you're going to get a 1 plus 1 and then a minus 1/5, another minus 1/5. So that's 8/5 inside the brackets, multiplied by 1/2, you get 4/5. All right, so that finally is the end of 15.5. So I hope this video wasn't too long, but I wanted to get in as much as I could here.